It's mysterious and wondrous. Welcome to the world of relativity. The Lorentz transformation intertwines time and space, bringing us a new understanding of the properties of spacetime. In the Lorentz transformation equations, if the velocity v exceeds the speed of light, the factor guang becomes an imaginary number. This leads to spatial and temporal coordinates also becoming imaginary numbers, rendering the outcome nonsense. This demonstrates that Lorentz transformations are not applicable for motions faster than the speed of light. The trajectory of an object in spacetime coordinates, or its world line, reflects its velocity. Velocity is determined by the ratio of change in time coordinate to change in spatial coordinate, essentially the reciprocal of the slope of the world line in spacetime. The impossibility of surpassing the speed of light suggests that on any segment of the world line, the change in time t must always be greater than the change in space delta x. Contrary to our intuitive belief that an object's speed can increase indefinitely, the concept of a speed limit set by the speed of light is coherent within the framework of special relativity. The principle that no object can surpass the speed of light has become a cornerstone of modern physics, and it introduces no paradoxes. In future videos, we will further explain why, despite continually increasing an object's momentum, it still cannot surpass the speed of light. In Alice's frame of reference, if two events share the same time coordinate, we would consider these events to be simultaneous. Using the Lorentz transformation to shift from Alice's reference frame to Bob's, we find that the time coordinates of the two events are no longer the same. In the new reference frame, event A occurs later than event B. According to the Lorentz transformation equations, the time difference in Bob's reference can be calculated, which is related to the spatial distance between the two events in Alice's reference frame and the speed of Bob relative to Alice. In environments familiar to us humans, this time difference is very slight. Even if Bob flies from south to north at 10 times the speed of sound, the events perceived as simultaneous at the poles by people on Earth, in Bob's view, have a time difference of only 0.5 microseconds, which is 5 times 10 to the negative 7th power seconds. When different velocity values are substituted into the Lorentz equations, event A might occur after event B, simultaneously with event B, or even before event B. This is what is referred to as the loss of simultaneity. Therefore, to accurately describe events as simultaneous, it is necessary to specify in which reference frame this simultaneity occurs. The loss of simultaneity leads us to ponder a question. If event A occurs before event B, then event A could potentially cause event B. In another frame of reference, if event A occurs after event B, then event B could potentially cause event A. Their causal relationship is reversed in different reference frames. Does this mean that special relativity disrupts causality? The answer is no. This involves another characteristic of the Lorentz transformation, the preservation of causal regions. In Alice's frame of reference, two world lines of light passing through the origin in both leftward and rightward directions are sketched. These lines are perpendicular to each other, each with a slope of 1. They divide spacetime into 4 distinct regions. In the region above, the time coordinate is positive, and the absolute value of the time exceeds that of the spatial coordinate. This region is termed the future light cone. Starting from the origin, any point within this region can be reached at sublight speeds. Thus, the event at the origin can potentially affect any spacetime point here. In the region below, the time coordinate is negative, and the absolute value of the time exceeds that of the spatial coordinate. This region is termed the past light cone. From any point in this region, it is possible to travel to the origin at sublight speeds, indicating that any spacetime point within this region can potentially influence the event at the origin. For each point in the regions to the left and right, The absolute value of the time coordinate is less than the absolute value of the spatial coordinate. Establishing a causal relationship with the origin would require superluminal travel. Since superluminal speeds are not permissible under Lorentz transformations and are physically unattainable, events in these regions cannot influence, nor be influenced by, the event at the origin. They are lateral regions. These four regions delineate different causal relationships with the event at the origin. Events within the future light cone may be consequences of the event at the origin. Events within the past light cone may be causes of the event at the origin, while events in the lateral regions cannot causally interact with the event at the origin. Let us examine how these four regions are altered under Lorentz transformations. Although the coordinates of each event point in spacetime are changing, each point remains constrained within its designated causal region, never shifting from one region to another. From any event in spacetime, the corresponding four causal regions could be constructed. Under a Lorentz transformation, although the positions of the event and its four causal regions would change, each point within a causal region consistently remains within its boundaries. All these demonstrations affirm that the causal regions of an event are preserved under Lorentz transformations. It is impossible to reverse the causal relationships between events by merely changing reference frames. With the help of a spacetime diagram, the concept of length contraction can be demonstrated more clearly. Create Alice's frame of reference. In this frame, there is a pole lying along the x-axis. At time 0, one end of the pole is at the origin O and the other end is at P, with the pole having a length of L. The pole remains stationary in Alice's frame of reference. Therefore, the world lines of the two ends of the pole are vertical. Convert the spacetime into Bob's reference frame using the Lorentz transformation, while Bob is moving to the right relative to Alice at velocity v. In Bob's frame of reference, the pole is no longer stationary, but is moving to the left, so the world lines of the pole are tilted to the left. How do we measure the length of a moving pole? When measuring the length of a moving object, the positions of the two endpoints must be measured simultaneously. In Bob's frame of reference, lines of simultaneity are horizontal. The point that has the same time coordinate as point O is Q, not P. According to Bob, the length of the pole should be the length of OQ, which we denote as L'. Let's calculate the length of OQ. First, we list the Lorentz transformation equations that convert the coordinates of point Q from Alice's reference frame to Bob's reference frame. Replace T' and X' in the equations with their actual values in Bob's reference frame, which are 0 and L', respectively. Returning to Alice's frame of reference, the spatial coordinate of point Q is the length of the pole in Alice's frame, L. Replace X in Alice's frame with the actual value L in the equations. Treat TQ and L' as unknowns in these equations. Solve these equations to find the values of TQ and L'. L' equals L multiplied by a factor less than 1, so the length of the pole in Bob's reference frame is shorter than in Alice's reference frame. The term length contraction can be misleading if not understood correctly. From the above analysis, we can clearly understand what length contraction means. An object stationary in Alice's reference frame will have a shorter length when measured in Bob's reference frame, provided Bob is moving relative to Alice along the direction of the object's length. Let's use a spacetime diagram to demonstrate the concept of time dilation. Plot Alice's frame of reference. Alice remains stationary within her frame of reference, and her world line is vertical. From event O to event P, the time she perceives as passing is Tp. Convert the spacetime into Bob's reference frame using the Lorentz transformation, while Bob is moving to the right relative to Alice at velocity v. Bob experiences the time from event O to event P as T'P. List the Lorentz transformation formulas for the coordinates at point P. In Alice's frame, the spatial coordinate of point P is 0, We are only interested in the time component, t prime p. From event O to event P, Bob perceives the time as t prime p, which is Alice's perceived time tp, divided by a number less than 1. Hence, Bob perceives a longer duration, feeling that Alice's clock is running slower. This is what we call time dilation. A key point here is that both events have the same spatial coordinates in Alice's reference frame. From the above analysis, we can accurately describe time dilation effect between different inertial reference frames. In Alice's frame of reference, if two events share the same spatial coordinates, then compared to other inertial frames, the difference in time coordinates of these events in Alice's frame will be the smallest. We can also describe time dilation from another perspective. Bob's reference frame is an inertial frame, and Bob will find that the internal clocks of any moving objects are slower than his own clock. A classic example of time dilation involves muons traveling through the Earth's atmosphere. Muons are produced by cosmic rays in the atmosphere and typically have a very short lifespan, around only 2.2 microseconds when at rest. In such a brief duration, according to classical mechanics, even if muons could travel at the speed of light, they would only cover a little over 600 meters, hardly enough to reach the Earth's surface. However, experiments have shown that many high-speed muons do indeed reach the surface. Convert the spacetime to the Earth's reference frame. Since muons maintain a high-speed motion relative to the Earth, their lifespan appears extended in this frame, and the distance they can travel during their lifetime becomes substantial enough to traverse the atmosphere and reach the surface. One might wonder, in the muon's frame of reference, why it can traverse the thick atmosphere in its brief lifespan of only 2.2 microseconds. This is due to length contraction. We mark the space traversed by the muon in the Earth's frame, then switch back to the muon's frame. To the muon, though its life is short, the rapidly oncoming Earth's atmosphere, due to spatial contraction, appears only a few meters thick, which is sufficient for it to traverse within its lifespan.